Probably. All right, so today's the day you all get so happy because limits are gone and we learn the power rule. So the very, very first rules you learn in calc are the constant derivative and the power derivative. So the derivative of a constant is always 0. The derivative of a constant is always 0. Did you staple your papers wrong? Yep, you're correct. And then the power rule says that whatever the exponent is, we bring the power down in front, and then we take one away from the exponent's power. So a quadratic's derivative becomes linear. A linear derivative becomes a horizontal line, and a horizontal line's derivative becomes 0. Because again, a derivative is a rate of change, and the rate of change is decreasing by 1. So the derivative of x to the 4th becomes 4x cubed. Now, if you have a constant in front of your variable, when you bring the power down, you just multiply the power by the constant. So here the power is 3, so 12 times 3 is 36. Subtract 1 away, and you get y squared. Yes, but we're not with the limits. So we'll start finding left and right hand derivatives algebraically. So this is actually something we talked about the other day. This was that limit of a constant, and I was trying to show you why the limit of the constant was 0. And this is the proof of it using the definition of the derivative. So we had the limit as h approaches 0 of f of x plus h minus f of x all over h. That is still the definition of the derivative. Now, however, we can use the constants and the power rules instead of the definition. But the reason the derivative of a constant is 0, if you look at the definition, is because you get 0 over h, and 0 divided by anything is 0, so the h sort of goes away and you get the limit as h approaches 0 of 0, which is 0. So let's use the power rule to find the derivative of the following function. So we write our notation as f prime of x. So you're going to put that prime between the f and the parenthesis. So f prime of x stands for the derivative. So the derivative of f of x becomes f prime x. The derivative of 3 is 0. The derivative of negative 2x is negative 2 times the power, which is 1. And then the rule is that you do the original power minus 1. So you get 1 minus 1, which is 0. Anything to a 0 power is what? 1. So really that negative 2x just becomes negative 2, because that becomes 1. And then you have 4. Bring down the powers, so you bring down the 2 and subtract 1 away. So we get plus 8x. So the derivative is negative 2 plus 8x. You do not have to show all the work. It's just for those that don't know the rule. Yeah. All right, there's a hot. I mean, he said it. All right. All right. So here we have d dx of 1 over x cubed. So what we do is we take the exponents out of the denominator and bring them up as negative exponents. So the d dx stands for the derivative of the function with respect to variable x. So this is the same as d dx of x to the negative 3 power. So the power rule still applies. You bring the power down in front and you subtract 1 away. So this becomes negative 3 x to the negative 4th, but we like our variable powers to be positive. So you get negative 3 over x to the 4th. Yes. It would still come up. So like, let's say instead of 1, that was 4 over x cubed, then it would become 4x to the negative 3. And then you would still just multiply the same. So you'd have 4 times negative 3, x to the negative 4th. So you'd get negative 12 over x to the 4th. And the variable goes to the bottom, but the coefficient stays up top. You could simplify the, yeah, we're going to get there. Maybe in the, like on the next page, I think. Okay, how about a square root? We don't have a rule for a square root, but what do we know about a square root function? Go ahead, Alex. Yeah, so square roots, cube roots, etc., we have to rewrite them as exponential powers. And then the power rule is still the same. So it's 1/2 x to the 1/2 minus 1. So you get 1/2 x to the negative 1/2, which is 1 over 2 square roots of x, or 1 over 2 x to the 1/2. I don't care if you write the square root or if you write the 1/2 power. They mean the exact same thing, so both are fine. Everybody feeling good? No, you're good. I know the boys know, like the power rule more, so that's why I'm making sure I'm not going too fast. Oops, yep. Because it was a negative exponent. Exactly, because it was like a fraction, so. All right, now the next example is not a power rule because you have a function inside. So we cannot take the derivative of a function to an exponent. We have to first use algebra and FOIL it. So you have to change. So it's d dx of x plus 5 times x plus 5. And then you have to FOIL the x plus 5s. And just like we write the limit, until I take the derivative, that d dx follows my problem. So technically the derivative of x plus 5 squared is the same as taking the derivative of x squared plus 10x plus 25. So we get 2x plus 10. So a quadratic becomes linear. A quadratic becomes linear. Are we okay? So that is, so instead of writing out like the words find the derivative, d over dx means to take the derivative with respect to variable x. So if I had d over dz, then my problem might be 2z squared plus 11z. Because now you're taking the derivative of that function with respect to variable z. So the variable here needs to match the variable in the problem. Yeah, hun? So these are written as f of x. So that's why there's no f prime. You could write f prime of x if you wanted. It's just that this didn't start with like f of x equals x plus 5 squared. Do you know what I mean? So it's just it's a notation thing. So I'm trying to show you like all the different varying notations. No. Okay, and then again, I say in calc, everything's going to always relate back to a tangent line. So the question is, does this curve have any horizontal tangents? So where would a horizontal tangent occur? Deja? So more specific than that, what do you think, Desiree? A max or a min, which, Alex, do you know what I'm looking for maybe? So where, like, what happens at a max or a min that we could calculate? The slope is 0. So what we're looking for is where does this derivative equal 0, right? So the idea would be a horizontal tangent occurs when y prime equals 0. So we need to find y prime. So what's the derivative of x to the 4th minus 2x squared plus 2? Go ahead, Desiree. Good. And so now you have two choices. You can either take out your GCF and then set it up equal to 0, or right away you can say, okay, the horizontal tangents will occur when this equals 0. So this graph has 3 horizontal tangents, which you told me the horizontal tangents occur at the max or mins, right? So wouldn't it make sense that a quartic would have 3 max or mins? So you guys have one less extrema than your power. Well, the reason that you have one less extrema than your power is because your derivative is cubic, and that's where the zeros of the derivative occur. I know, right? Like math just makes sense. So you know how we talked briefly about graphing? If you were to take your calculators and you were to put the original function in y1 and the derivative in y2, everywhere the original function had a max or a min, your derivative will cross the x-axis. So like at -1, 0, and +1, our derivative will be at 0 on the graph, and the original will be at its extrema. Yeah. So like it'd be something. It could look something like that. But yes, this would be like your derivative graph. So now we're going to talk about the fact that everywhere the original has an extrema, the derivative will have a 0. Always. Okay. So that's all right. So, oops, wrong PowerPoint. Yeah, earlier today we did the derivative of a constant and derivative of a power. The second rule we're going to look at is the product rule. I opened the same PowerPoint twice. I so did. So the power rule is the way we set up and look at our problems in general and forever from here on after. The product rule would allow us to do that one example we looked at where we FOILed it, where now we didn't have to FOIL it. We could do a function times a function. So we want to determine if this statement is true. Is the product of the derivatives equal to the derivative of the product? So product of the derivatives would look like f prime x times g prime x. Is the product of the derivatives equal to the derivative of the product? Meaning like FOILing out f times g. So we want to determine, is that true? So in order to do that, we're going to take two functions and we're going to find their derivatives, and then we're going to find their product and its derivative. So go ahead in your table, find the derivative of f and g. So the derivative of f is 4x, and the derivative of g is 4. So 4 times 4x would give us 16x. So that's the derivatives products multiplied together. F of x times g of x looks like this. So what we're going to do is FOIL f times g and then find its derivative. So 2 times 4 is 8x cubed minus 2x squared plus 12x minus 3. So the product of the original, and then what we're going to do is find the derivative of that. So the derivative of 8x cubed is 24x squared. Derivative of 2x squared is 4x. And derivative of 12x is 12. And derivative of negative 3 is 0. So is the derivative of the product of the functions the same as the derivatives product? No. Those two do not equal each other, right? So that leads us to the product rule. So you cannot take the derivative of two functions and multiply their derivatives together. So if you wanted to know what the derivative of f times g was, you have to multiply the originals and then find your derivative, or you can use the product rule. The top is correct. This is incorrect. So the either way is to FOIL the originals or to use the product rule, which we haven't learned yet. So we can see from that example that they are not equal. So that leads us to the product rule. So the product rule says the derivative of a product is the first function multiplied by the derivative of the second plus the second function multiplied by the derivative of the first. So d dx of f of x times g of x is equal to the first times derivative of the second plus second times derivative of the first. So when I say first and second, I'm talking about the order with which the functions are written in the multiplication. So it's the first times derivative of the second plus the second times derivative of the first. The product rule says the first times derivative of the second plus the second times derivative of the first. So if you take that function we just had, d dx of f of x times g of x, in terms of the product rule, would have looked like f of x, which is 2x squared plus 3, times the derivative of g of x, which was 4, plus g of x, which is 4x minus 1, times f prime, which was 4x. To FOIL it? Yes, and that's what we're going to talk about. Like there are times where FOILing it's easier, or the product rule is easier. And that's kind of like why I show both. Because you're right, like now we had to take our derivatives and still distribute and clean up. But you can see how you get the same answer both times. Oh my goodness. The net we score on twice. Now I need to know where my seats are. Below. Like we're like 3 rows off the ice. But her seats. All right. So let's, oh, I just ripped my new textbook. Let's do this example using the product rule, even though I know sometimes FOILing might be easier. So we're going to do the first and the second, and I'm going to do them in red and blue, kind of just to help you as I go through. So the derivative would be y prime equals the first, which is x squared plus 1, times derivative of the second. So derivative of x cubed is 3x squared. Derivative of 3 is 0. So first times derivative of the second plus the second times derivative of the first. So derivative of x squared is 2x, and derivative of 1 is 0. And then we're going to distribute and combine like terms. So 3x squared times x squared is 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x, which equals 5x to the fourth plus 3x squared plus 6x. All right. Next. Oh, where's my square root down there? Isn't that weird? Like, why is it not in my problem? All right, so the square root of x plus 2x equals 2x squared plus 5. So once again, you could do this by FOILing or by using the product rule. So instead of having it as the square root of x, though, we would rewrite it as x to the 1/2 power. And then we would take our derivative. So it's the first times derivative of the second plus the second times derivative of the first. So that's 1/2 x to the negative 1/2 plus 2. Not until after you FOIL the other side, because like you're going to add or subtract the exponents together. So this becomes 4x to the 3/2, because when you multiply variables, you add their exponents. So 1 plus 1/2 is 3/2. And then 8x squared. And then here, 2 times 1/2 is 1. X squared minus 1/2 gives x to the 3/2. And then 5 over 2, x to the negative 1/2. And then 2 times 2 is 4x squared. And 2 times 5 is 10. Which is 1. 2 times 1/2 is 1. So you get 5x to the 3/2. 8x squared and 4x squared gives 12x squared plus 5 over 2 square roots of x plus 10. Oh, yep. Okay. So do you want to FOIL or power rule. The first thing I would do is bring up my 1 over x's. Honestly, this one with the negative exponents will probably be easier to FOIL to start, just because of all the negative exponents and the fact that you have so many variables and no constants. So the power rule is easier when you have like a variable plus a constant, because then you're only distributing. If you have variables and variables being added, then it's better to FOIL to start. So we'll do first. So x times x is x to the negative 2. Outer, inner, and the last. So what makes this nice is when you FOIL these, they all sort of clean up. Do you see how nice that is to FOIL? I will gladly do the power rule if you want to see it. Or the product rule. It's just very messy. Because now my derivative becomes negative 2x to the negative 3 plus 2x plus 1 plus 5x to the 4th, which becomes negative 2 over x cubed plus 2x plus 1 plus 5x to the 4th. Do you want to see it with the product rule? Did anybody start the product rule before I got here? Yeah, like I can do, I'll write it all out for you if you want me to. Is that a yes or no? Yeah. The product rule too? Sure. Is everybody okay with what's on there now? Because I'm going to erase it. Or Des, are you still writing? Yes. So I would still make this x to the negative 1 when I did my product rule. So the product rule would be the first times derivative of the second. So that's negative 1 x to the negative 2 plus 3x squared. So first times derivative of the second plus the second times derivative of the first. So negative 1 x to the negative 2 plus 2x. Now you got to FOIL twice. So it's the first. So you get negative 1x to the negative 3. And then you get 3x. Then negative 1 x to the 0, which is just negative 1, plus 3x to the 4th. And then you got to FOIL the second part. So you get negative 1 x to the negative 3 plus 2, because x to the negative 1 times x to the 1 is x to the 0, which is 1, minus x plus 2x to the 4th, sorry. Now you combine like terms. So negative 1 and negative 1 gives you negative 2 over x cubed. 3x to the fourth and 2x to the fourth gives you 5x to the fourth. Positive 2 and negative 1 gives you 1. And negative x and positive 3x gives you 2x. And remember, the order you add or subtract and doesn't matter. So the order we write them didn't matter. You can see it's identical, but do you see how like actually foiling to start made this problem easier than the product rule? You missed the other one. Good. So again, it's not wrong. There's not a right or a wrong. One is just messier. There's not a right or a wrong. One's just messier. And then honestly, the last part of this is super easy. It's just the notation. So we can take derivatives until we get to 0. You can take a derivative of a function until you get to 0. So we can represent derivatives in a variety of ways. So we started by talking about the ddx's, right? A lot of times, instead of ddx, you might also see dy dx, which means the derivative of y with respect to variable x. So if you had like a y equals function, then it would be dy dx. The second derivative is d2y dx squared. So it means the second derivative, that's where the 2 up top comes from, with respect to variable x twice. So d2y dx squared. So what do you think the third looks like? Over. Good. And then the fourth. Perfect. The notation we know or see the most is f of x. We always say f prime. Technically, the derivatives, when we're writing this, although we use the apostrophe, they're actually Roman numerals. So after you get beyond 3, it's IV, exactly. It's a Roman numeral. It's not 4 tick marks. You go to the Roman numerals. That's similar to if you were using the variable y. So like if you wrote y prime, it would also be like y double prime, y triple prime, and then y IV. Sometimes you see it with a capital letter D and then a subscript 1 and then a 2. Now the D to the subscripts are the actual numbers. So you could ask for or see something say like D to the 99th which would be the 99th derivative. And we'll get into that a little bit more with trig functions. The 99th derivative of a trig function is not 0. And then if you're talking about physics, the original function is position. The first one's velocity, good. So jerk, if you think about a car accident, it's the whiplash that occurs. It's position, velocity, acceleration, jerk, snap. I don't know what happens after snap. I'm just more special. Is everybody okay with the chart? We're not going to do too many of the higher order derivatives. It's just that one of them occurs like in our homework. So, it's nice to see. This is an easy power rule, right? So f prime becomes what? You would. Yeah, so it's 3t squared minus 12t plus 9. What's the next derivative? And the third derivative? And the fourth. You can take the derivative as many times as you can till you get to 0. And that's what I was saying. A trig derivative and an exponential and a logarithm have no end. So, like, those derivatives will never get to 0. Exactly. There's a cycle, yes, but not all odds. You'll see. We'll get there. We'll get there. All right, your homework's going to be in the book. I'll write down the problem numbers for you. Is everybody done with this example? Oh, that's really hard to see. So it's on page 129 in our new books. We'll look at 1 to 6. Some of them will be odds, but not the first 6. 7 to 11 odd. Actually, you can do 7 to 13 odd, because I'm going to make you do 13 anyways.
Yeah, I know. This is the worst whole time.
Well, 15 and 16 came from a new set of directions, so that's what made me like 15, 16, yes. And then I literally just lost on the page. I want you just to do one of the 33. So that way you guys can, I'm trying to give you majority odds so you can check your answers. So then tomorrow you can just come in, and if you have any questions, we'll go over your questions.